weight is acting on what?
From B to the center of the Earth, from the center of the Earth to B.
They don't have to be right over top of each other. I mean, you can if you want to sort of extend the ground and then draw the arrow there, that's fine. All right, there's one pair.
From A to the ground. From the ground to A.
Even though it's really coming from the entire planet, like treating this all as one object, probably should have put hash marks in here. Just the flat Earth. All right, done. Normal force.
From A to the Earth to A.
The normal force going down.
Yeah.
It's going up.
Normal force is repulsion. It's keeping them apart.
Yeah, but A is pushing. It's pushing down on the Earth.
Yeah,
Which
we
is
would
back.
draw it down there.
Oh.
Because A is pushing down on the Earth,
Hmm.
and the Earth is pushing up on A.
Oh.
I assume you were saying it differently than what I just drew.
That's what I meant. I
Oh,
guess I was saying
okay.
it wrong.
There's another pair of normal forces.
Between A and B.
The A and B aren't touching.
Alright.
Between.
I feel like this is wrong between B and the rope.
We don't know how the rope is connected to B, and that's what we're calling tension.
Right.
If I had more detail, we could narrow it down. There's one of the videos that talks about how there's no such thing as tension. Tension is sort of a catch-all in this situation since we don't know how it's attached.
Then between the earth and the rope, or the earth
Yeah.
slash pulley and the rope.
There's a reason the rope is bent like this. So I did not give you enough information for you to know exactly the direction of this force, but there's some force somewhere in that direction. We'll call it y sub r, and then acting back y sub r. Don't think it's somewhere where there's contact. It's going to be somewhere in this region right here. Just pick someplace near the middle. All right, so we got normal force done. Oh, what about B in the ground?
There's no contact.
Right. The two most common things, sometimes people like doing normal force here, and sometimes they'll do normal force here. All right, tension. Obviously, we've got a tight rope now. It pulls. So on this end of the rope, which way is tension acting?
Towards the center of the rope.
Towards B.
Towards B.
Oh.
And then on B.
Towards the rope.
Something's holding B up. If I cut the rope, this would disappear. So the rope is pulling up on it, because B would be in free fall otherwise. And then what about over there?
On the rope towards A. A towards the rope.
Now notice I have those extra subscript here. I'm treating this tension and this tension the same. If you want to put subscripts, these would have the same subscript. These would have the same subscript. Those are the pairs. If it is an ideal rope, those tensions are the same. So just keep in mind, later on when we do away with the frictionless aspect of it, the tension on each end will not be the same anymore, but at this point the tension is the same. And friction.
Between A and the ground.
Which way is it acting on A?
It would be
Away from B?
As in left?
Yeah.
Which way, the way to think about it, if this were frictionless, which way would A move?
The right.
Therefore, friction wants to oppose that, and it acts to the left on A. So that's the friction. I'll just put A, even though there's not another friction pair. Where's the other part of that pair?
A acting on the ground.
Now, from a solving point of view, the ground has all sorts of forces. We assume if it's a real planet, it's being pulled in all sorts of directions. Realistically, what would happen next in terms of the entire process is we would concentrate on those forces and those forces, given that the tensions are the same. And we could then, if I knew B and if I knew a couple pieces of information, we could predict the acceleration of the two objects. But that is for another time.
So if we see something like this on a test or on a quiz, are we expected to do the forces for bodies that aren't labeled? I wasn't expecting us to be labeling forces on the rope.
Okay, so there will be on the second test, test 1B, there will be what I call the complex force diagram problem, where you will do the forces on the rope and so forth.
Okay.
One of the reasons we do forces on the rope is later on when we get rid of the friction, the frictionless aspect of it, make it slightly more real, it will matter. But if this were just a simple problem and still an ideal rope, and I gave the setup and said, what's the acceleration of the masses? Acceleration scalar, since they're moving in different directions, you only really have to do the parts that matter to the problem itself. So if I specify that I want to do a force diagram, such as that's a part A, I would have to tell you specifically. Because otherwise, well, yeah, these are the big objects here, but I could do a force diagram where I split A in half, and I got the left half of A and the right half of A. Or take it down to the atomic level. I don't want to do that. That is the path to madness. And there's enough other things in here that will get you on that road. I was once at a dinner with a couple other physicists, including some professors, and we started looking at serial killers, the similarities between serial killers and physicists. It was, there were some similarities. This is almost if that, going down the road and you're thinking, all right, serial killer, physicist. Which one am I gonna do?
Anyway, the similarities.
Tend to be loners. Socially awkward. That was the big one right there.
So pretty much engineers in most STEM majors.
Yeah, I think you could probably make that argument. Not geologists. I think geologists are probably the cool ones.
Oh yeah. No, I lived in New Mexico. You meet a geologist who was like out there hunting for oil or doing whatever. They always had, the Indiana Jones hat, and they were very outgoing and adventurous.
But they have the word subparallel. You know what subparallel means?
No.
Not really parallel. It's one that my wife did geology. She was a geology major. And she said, it makes a lot of sense why you'd use the word subparallel. I said, but doesn't it just mean that it's not parallel? Yeah, sure. Rock faces like that. That's subparallel. From a physics point of view, it's just not. Anyway.
Oh, so it's kind of parallel?
Yeah, but not really. Yeah.
Close enough.
See, at that point, I think from a physics point of view, you would go close. You would say close enough to parallel. Let's just assume it's parallel, as opposed to giving it a different label. It's an assumption. Anyway, that is it.